Now we are going to talk about EMF devices. These are parts of electric circuits which supply energy to the other parts. There can be many different kinds. Batteries are the most well-known examples. They convert chemical energy into energy usable by the charge carriers. The power supplies that you use in your labs, that would be another example. In the case of power supplies, the source of the energy is very complicated. The energy is coming from the mains electricity, but the original source might be a hydroelectric power plant or a thermal power plant or a nuclear power plant. It just varies. Sometimes there's a mixture. So there's something very complicated behind that simple looking symbol actually. But of course, for the purpose of analyzing a circuit, we don't need to know the physical picture behind this symbol. We only need to know a few of its properties. Okay. Before going on, let me talk about the name in here. The EMF stands for electromotive force. This is a name given in the 19th century. At that time, people did not have any idea about what the physics of electric currents are. So as a result, they just give a wrong name. Misnomer is a term that we use for these kind of wrongly named things. So that's an example of a misnomer. But of course, the name is stuck. So nowadays, we would like to evade this long form and we just call them as EMF devices. So as a result, I will always use this shortened form, EMF, and never use this electromotive force form. Okay, so as I said, these are energy sources, so they give energy to the charge carriers, and we would like to describe how much energy they give. And in that way, we define the EMF of the EMF device. So first, there is a polarity of the device. So there's a positive side and a negative side. So let's just call this as positive side and negative side. So in electric circuit, of course, positive side is shown with a longer line in here. And so the idea is this. If a charge carrier passes over this device, some energy is given to the charge carrier. And we would like to quantify this amount of the energy given. So I'm going to think about this kind of a situation. So first we draw an arrow. So this is the arrow that we draw. So we just draw the arrow in the same direction as the polarity of the device. Okay. And we say that if a charge Q passes over the EMF device along the direction of that arrow, then the energy given to the charge carrier is proportional to that charge. And so therefore it is charge multiplied with a constant. So the constant in here is called the EMF of the device. So E is the EMF of the device. It's essentially energy per charge of the charge carrier. So energy per charge. So as a result, its units are in SI, it is joules per coulomb. But if you remember, we have just called this unit as volt. So therefore, the EMF is a quantity that is measured in volts. Okay, but of course, you have learned about this device as a device that supplies, that makes sure that there is a constant potential difference between its terminals. So we are going to show that based on this definition, we are going to show that that's also true, that indeed the potential difference between the terminals of that device is equal to the EMF. But that's a secondary fact. What's important in here is that this is a source of energy. So as a result, we just define the EMF of the device, that fundamental property of the device in terms of the energy. So EMF is energy given to the charge carriers per unit charge of the charge carriers. So it's just you can think of it as a coincidence that it has a unit volt. Okay, so So that's the fundamental definition. So you might wonder, what if the arrow is drawn in the opposite direction? So what if the charge carriers pass the device in the opposite direction to the polarity? The answer to this is actually very simple. We can think of this as a charge minus Q passing in the correct direction of the polarity. So therefore the energy given to the charge carriers, so the charge carriers that have crossed this device is going to have an extra energy which is equal to that charge multiplied with the EMF. So in that case, the energy given to the charge carriers would be minus Q times E. So in any case, you can see that in either case, the energy given to the charge carriers might be positive or might be negative. Okay, so in that case too, we are not implying that this Q has to be positive. It is possible that that quantity Q might be negative, which means that along the direction of the arrow, the current is negative, in which case energy given to the charge carriers would be negative. That would correspond to a situation where a positive energy goes into the EMF device. So when you are charging a battery, for example, this is the situation that you are having. Okay, after the energy, we just described the power. So again, we are going to draw the same picture in here. There's a current passing along that direction where the arrow is drawn with the correct polarity of the EMF device in mind. So in that case, in time delta t, the amount of the charge that passes is I times delta t. Right? This crosses the device. It just passes the device. So therefore, the amount of the energy given to the carriers is equal to Q times EMF. So therefore, this is IE times delta t. And so therefore, the power of energy that is given to the carriers is basically the rate of change of the energy of the charge carriers. So that's given as I times E. So therefore, let me just write this thing down like this inside a box. It's the power supplied by EMF device to the charge carriers. Okay. So in the usual operation, this is positive. The EMF device gives energy to the charge carriers. But as I said, when you're charging a battery, for example, this can be negative, in which case the battery gives negative energy to the circuit, or an equivalent way of saying this is that the battery takes positive energy from the circuit. So that's also a possibility. Let's go ahead. Okay, so there are these two simple examples in here. I just give these examples so that I can multiply two numbers. So in this situation, for example, a current passing through the EMF device parallel to the correct polarity. So therefore the current is positive, and of course the EMF is also a positive quantity. In here, let me write the power supplied by the EMF device is I times the EMF. So therefore this is 2 times 6, this is 12 watts. Right? In that case, this EMF device supplies positive energy to whatever is in here. So therefore, the EMF device loses energy, that thing gains energy. The charge carriers carry the energy from the device to whatever is in here. Okay, let's go to the second example. In the second example, we have more or less the same kind of a thing, but this time the current in the opposite direction is a positive quantity. So 3 ampere current is flowing like that. In that case, I can describe this as, let me change my pen. I can describe this as a current which is flowing in the other direction which is minus 3 amperes. So the current that flows in the direction, in the correct direction with polarity is therefore minus 3 amperes. So in that case, the power supplied for this example would be minus 3 amperes multiplied with 5 volts. So therefore, this is going to be minus 15 watts. Okay, so that's the situation where, in this case, you are charging this battery. So therefore, there is a source of energy in here. So this black box in here somehow should contain some other EMF devices, some other sources of energy in here. So these things produce energy. Charge carriers carry that energy and give it to that EMF device. Next, we are going to prove the relation that we have known all along. We are going to show that the potential difference between the terminals of an EMF device is equal to the EMF. To show this, we are going to use the conservation of energy statement. Essentially, I'm just going to consider this kind of a circuit, right? So the EMF device is connected to a black box device in here. So the points A and B are like that. So EMF produces some energy, gives this energy to the charge carriers, and these charge carriers carry that energy to the black box device in here, and they consume that energy. So I'm going to write down the conservation of energy statement in here. Okay, so the conservation of energy statement is that the energy produced by the EMF device should be the same as the energy consumed by the black box device. So we can also express this in terms of not the energy but the power. So I can cross the energy statement in here and then write power for each side. So the power produced by the EMF device is equal to the power consumed by the other device. So we have formulas for both of them. Power produced by the EMF device is, I'm going to say that the current is equal to I. So I'm going to take this arrow in here. So this is along this direction, the current is I. So the power of energy produced by the EMF device is I times E. For the case of the power consumed by the black box, it is I times the potential drop, and in that case the potential drop is the potential difference AB is VAB, which then implies that EMF is equal to VAB. I mean, if there is a non-zero current flowing, then the potential difference VAB, that's the potential difference across the terminals of the EMF device, that's given as the EMF. Okay, so this is actually a very simple matter to show that the EMF device maintains a constant potential difference across its terminals, but the energy production property of the EMF device is more fundamental than this. Okay, and then we have real EMF devices. What we have described up to now is just an ideal EMF device. In the case of a real EMF device, there's always an internal resistance which is connected parallel to the connected in series to the EMF device. There's actually a theorem called the Thevenin theorem in electrical circuits, which says that any kind of a DC circuit with two terminals can actually be represented like this as some kind of a ideal EMF device connected in series with a resistance. So you can think of this as a property of the such EMF devices. Okay, so why is this so significant? Because in that case, if you think of these 2 points as the terminals of the EMF device, in that case, the potential difference across these two terminals, they do not need to be they do not need to be equal to the EMF. Why? Because there is a potential drop on the internal resistance as well. So let's consider the situation where the current is flowing like that. Again, this is point B and this is point A. If I take this point as C, I know that the potential difference is VCB is equal to the EMF. And I also know that potential difference VCA is equal to I times R from Ohm's law. So as a result, the potential difference, let's say VAC is equal to minus IR. If I add VAC together with VCB, that I'm going to get VAB, so that's VAC plus VCB, so that's minus IR plus EMF. So therefore, the potential difference across the terminals of the real EMF device would be equal to EMF minus I times R. So as a result, the potential difference across the terminals of the EMF device depends on the amount of the current that passes over it. More current passes, the potential difference is more different from the real EMF. Only in the cases where the current that's passing is extremely small, you can measure the ideal EMF value.